Nonlinear oscillations. Let's make a few general remarks about nonlinear oscillations. First, most of oscillations in nature are nonlinear. Second important thing to note is that with nonlinear oscillation there is no superposition of solutions. We will see that nonlinear oscillations have a lot of new phenomena arise, such as frequency doubling or tripling, bistability of motion, chaotic motion, and so forth. It should be noted that nonlinear oscillations received renewed interest starting from roughly 1970s due to availability of computers. I would like to point out one specific new phenomenon, which is known as limit cycle. Limit cycle is usually demonstrated by considering so-called Vanderpoel Oscillator. Here's the equation for Vanderpoel Oscillator. Second derivative of x, the dynamic variable, plus mu, some parameter. Then we have x squared minus 1 times x dot plus x equals 0. Note that this equation has nonlinear damping, and it's not energy-conserving system. For example, it describes oscillations in vacuum tubes in electronics. What is limit cycle? With linear oscillators, we are familiar with attractors. For example, if we have our normal oscillator, which has quadratic potential, u as a function of x, then we have a stable point, x equals 0, and velocity equals 0, such that our orbits tend to go around this attractor, and if we happen to have any kind of damping, they will slowly tend towards the stable equilibrium. So this point here, x equals 0, x dot equals 0, will be an attractor. On the other hand, limit cycle is not just a point in phase space. Limit cycle acts as a stable attractor for a whole closed trajectory. Here's an example of phase space trajectories, x and x dot, of Vanderpoel oscillator when mu is equal 1. As you can see, various trajectories that start from various points, either from inside this loop or outside of this loop, tend to go towards this special trajectory, as shown in bold blue, which is the limit cycle. Limit cycle, we can define it as a stable attractor-like cycle or closed trajectory. This stable attractor-like closed trajectory, as we can see, is when time goes to infinity. All of the trajectories tend to go towards this particular closed trajectory, this particular limit cycle. Note that if we reverse time, then trajectories in phase space become unstable. Such limit cycles are very important for real-life oscillators. A great example of limit cycle that each of you possess is your heart. So your heart has a limit cycle because it has stable, closed trajectory that keeps repeating. For example, when a reanimator is trying to revive someone whose heart has stopped, he's counting on the limit cycle, on that stable, closed trajectory that any motion will tend to go towards. Again, such limit cycles can only occur for nonlinear oscillators.